Don't forget quite a lot. Happy Mid-On Festival for those who celebrated today. Very special Algos attend today because actually it's the coding solution for the Shang-Chi movie, which has been actually very good this year. So we're actually going to go over some ROC curves and near and dear to me, the Northeastern-based data science data mining techniques I learned. But I present to you in tonight's episode. Tonight's episode is obviously brought to you by the Mooncake, which is pretty awesome. Without further ado, here is the slide deck. As you can see in the slide deck, this is obviously a very special episode. It's regarding to the Lunar New Year. So here we go. Obviously sponsored by Zhongshujie, or like the Chinese Moon Festival, the Autumn Festival. As you see, this is a very awesome, lovely little mooncake. So tomorrow I'll air an episode on my personal YouTube that will actually show you how I critique a mooncake and then basically the general steps to make one. I did substitute live water for honey, and obviously because I want to be healthier, it's going to be mostly a lotus mooncake. So obviously, if you don't want to shell like 30, 40 bucks in a Chinese mart, you can make a mooncake from scratch. It's like a puff pastry with like some sort of filling in it. It's actually pretty cool. So topics for tonight. We have a very quick quiz about Python ROC libraries, or receiver operating characteristic. We have some coding basics for ROC. The problems A, B, and C, part of this episode, coding solutions demo. And then problem D, we do it 4 different ways. Decision tree, logistic regression, gradient boosting, and something called support vector machines, or SVM. Of course, for bonus content, we have advanced classifier models, where I don't exactly code the models, but I basically tell you what they do. And then after my Hawaii vacation, we'll have the season 2, episode 7, which is going to get into P versus NP and like some graph stuff. And here's the quiz. What is the Python library that we use for ROC curves? I'll give you guys 15 seconds to think about it. Yeah, it's very strange to be celebrating Zhongshujie during COVID. Like you can't even share the mooncakes. You can only like do virtual emojis and memes. It's weird. But it's just part of hybrid life, really. What really surprised me is like how many people actually want to make a mooncake during COVID. I guess baking is a thing, and people are really happy to make bakeries. Even my coworkers really like the mooncake, which is surprising me. So good. At least there's appreciation of Chinese culture despite the COVID situation. Yep. So the answer is, of course, scikit-learn, sklearn, however you name it. It's that. And of course, you want to use a stable version, as you see why later. So a note of lament, I know, big sad. No collab episode, unfortunately. I tried my hardest. I collaborated like almost 5 different like Northeastern friends, but due to COVID, busy work, whatever, post-grad, it's just not going to be possible to do a collab episode at this point. So instead, we're going to have another bonus episode in October, Halloween related, which is really awesome. So yeah, no collaboration episode, but we do get another bonus as like a way to compensate for that. So very simple ROC coding basics for basic ROC for dummies. As you recall from last episode, we got a really awesome ROC curve over here with TPR of 1, FPR of 1, a really crappy random classifier, 0.5 AUC value, and then the beautiful, almost perfect to 1 AUC value. So be very careful with what type of model you use for coding. For example, you can't, it's like basically when you're little, you have like fitting a block of either a square, triangle, or a circle, right? You can't fit basically square into a round hole here. So you cannot like use logistic regression for like a decision tree model, or you can't use gradient boosting for like logistic regression. You gotta stick with the model you use. So make sure you actually from the get-go actually use the right model, or the thing will simply not work. So we basically discuss it in 4 ways: decision tree, logistic regression, gradient boosting, and support vector machine. We have 4 different ways of like basically coding it. And of course, there are more advanced ways And of course, since we're doing a bit of random sampling here, every time we run the code ROC AUC score, it may generate a different type of AUC curve. And finally, of course, this is like Python, not architecture. It's not drawn to scale. So the TPR, FPR right now may be deceptively simple, but depends on the data set you're using, it might actually not be so simple. So before we can get to ROC, let's just go over the forward focusing. So of course, part A, review, you know, it's all about forward focusing, you know, the A amount of influencers, B amount of promoters, C amount of moment lovers, and D amount of advertisements. So we knew from episode 5 that like this answer is basically forward focusing with weighted edges, right? The coding is actually way more complicated. So we actually use the following coding structures to apply the forward focusing algorithm, which I'll show in the demo. You have something called Python Network X library, which is the library that we used before from the LeBron James Space Jam episode, to basically make a visual representation of a graph. And then for each layer of the graph network, we have A, Instagram influencers, B, Facebook promoters, C, WeChat moment lovers, and D, YouTube live stream of advertisements. We create a dictionary structure for each. Then we basically use a list structure to store each possible set of I, J, K, L nodes for each respective layer. And we basically apply forward focusing on top of it as boilerplate. There's a new structure called a deck, or a double-ended queue. And as a quick annotation, here is some drawing we'll be making for it. Let's say you have right here a nice little queue. And then let's just say you have something called the input of this queue and the output. So in a normal queue, like the single-ended queue, you know, it's a very basic structure of LIFO, right? Last in, first out. So you last put in something in the input, the first thing that comes out is the thing that you put in. However, in a deck, you have something that is more complicated. So say as an analogy, the deck is almost like a two-way road of like cars. And then you have some sort of like cars going this way. And then you have some sort of cars going this way. Now, of course, you can see what happens here. It's like a collision. Oh my God, horrible stuff happens. I'm talking about experience here with the car crash. So yeah, that's not what you want to see, right? So instead of worrying about the collision over here and just being crazy, the deck allows you to basically do a U-turn. So you're allowed to basically turn around before you collide with another car within the deck. So basically what the deck does, it's a double-ended queue. So you can basically put in anything you want as soon as you can also put out everything you want. Same here, we could put in whatever you want, and you can put out whatever you want. And you can see this is way more efficient than a regular old queue because of that. I'm actually going to clear the drawings now to demonstrate some more. Whoops, sorry. So yeah, the deck, as I shown earlier, is a double-ended queue. It's basically a doublet linked list implementation. There's no allocation, deallocation overhead, which means you don't have to worry about runtime with more allocation, deallocation. The complexity of all operations, you know, lookup, insert, delete, search is 01. And if you put it for an iterator or you try to insert and delete in the middle, it's also 01. However, random access, which actually gets into a bit of the ROC here, like basically randomly accessing a point in the queue is ON, because the worst case, your thing in the end, you have to search for all the items in the queue or in the deck. And the growing array, the amortized time complexity of all deck operations is 01. And then of course, the random access in that situation would be 01 as well, but the complexity for insertion and deletion in the middle is ON. So for those leak code lovers and algorithm interview experts, definitely remind yourself to remember this one before your next interview. Runtimes are super, super important. Yeah, here's a reminder of the graph, you know, a source, a sink, infinite edges on the outside, one on the inside. All right, part B. So now here's the matrix in question we had before from episode 5. You know how it looks. The coding solution is quite geometric. So we are given a matrix of the following. We're given a matrix of 33, 44, 55, 77, which has a positive determinant of 121. You know, 30 times 77 minus 44 times 55. We use the true positive rate, false positive rate, true negative rate, false positive rate. Oops, that should be actually not that. That's a typo. But typo aside, it's basically true positive rate, false positive rate, true negative rate, false negative rate, using the same functions we did before in episode 4. So we're going to first have the triangle area, find the triangle part of the ROC curve. And just as a quick sketch again, so I can like show you what I'm talking about. Let's say you have just this curve over here. You have ROC curve, somewhere like this. You have a triangular area here you want to like calculate. So that's a triangular area. You have like a trapezoid area here you want to calculate as well. That's a trapezoid area. And then the entire total area is what you want to calculate in the end. So you have 3 different Python functions for that. Using the concept of encapsulation, encapsulating the triangle area, trapezoid area, and the total area. Using, of course, Riemann sums. And we also have a message string for the total area, because if it's 0 affinity, we do basically have a flat line, which is not a valid ROC curve, with an exception. So yeah, part C. Okay, this is basically a rehash of the original. Basically, master user to upgrade Shang-Chi. It's not from the movie, it's just my own personal invention. And if you basically solve all the problems right, you get a perfect ROC value of 1. So matplotlib will make this a lot better looking by using something called the iris data set. So in the iris data set, you have basically 3 different colors to deal with. You have the iris versicolor, iris virginica, and iris, I don't know, there's another iris data set, 3 of them. So once you see that, you'll understand what I'm talking about. And then finally, part D, which is the most involved part of this actual entire episode, is basically trying to conquer the rest of the dragons with given AUC levels of 0.76, 0.56, and 0.99. We basically, yes, modify more or less low-key copy episode 5 code, but do it 4 times in a row differently. So I have all these different links that you can take a look at regards to decision tree, logistic regression, gradient boosting, and support vector model or machine classifiers. And of course, to make things more interesting, we have more advanced models. So the reason why we can't use the advanced models for the algos in general, because all of these are NP. All of these are not easy to find out polynomially. So for example, we try one-hot encoding, sure, but we can't exactly binarize multi-class data easily. We have to like do some crazy pre-processing, which goes way past the scope of the episode, which is like a basic overall refresher of ROC, not meant to be like a in-depth my data mining class 2.0 type of thing. We can also use SMOTI, and that's something we'll actually cover in episode 10. The SMOTI is best used with something that's more randomized. Oh yeah, episode 10, by the way, is actually going to be the NP completeness, the finale episode. In addition to that, the a priori bagging algorithm for classifications, just FYI. And that'll be probably around maybe November or sometime soon, like around Thanksgiving. So yeah, the finale is ending basically before Thanksgiving, just heads up. Also, we have the optimal decision tree classifier, which is upgrade from classic decision tree classifier. They basically optimize the decision tree. You have a random forest classification, you have a bagging classification. And here's some sources you can look at. So now I'm going to go over some terminology and then finally show you the coding demo. I've been speaking for like good 20 minutes or so, so time to finally show you some code. So encoding is basically conversion of a classifier label into numeric readable form. Regression is the model that shows the entropy of a data set, or like basically the leftover of the data set. The ensemble is a form of machine learning class of classifiers that built together to run a model, basically a collection of models to run. Pre-processing, the step to clean up dirty or basically unclean data. For example, NaN values, like null values, or even, I don't know, gibberish WebD values, whatever, just get rid of them. The concept of arrayable, which is the flattening of contiguous arrays. You see this picture down here, you have a 1 by n array. You do some sort of crazy processing here, which goes beyond the scope of the episode. And you basically turn the array to n times 1. Why is it not a transpose? Well, here's the thing. A transpose only turns the dimension of the array. The rainfall also flattens it contiguous, which means it basically changes the spacing of the array. So instead of it being an n block array here, it's basically a one block pasted n times down here. Without further ado, here is now the coding demo. So you see in the coding demo, I have some pretty solid code. So I'll just simply run piece by piece each part of the code. So yeah, of course, this is the slide deck, problem A. So this is the original picture for the graph representation. Here's me importing the network, and here is the solution for part A. Quite straightforward, actually. They have a graph collection, you have a graph structure with init and row. And you want to basically use a BFS, a searching algorithm, to find, do we have the optimal shortest path? If we do, you can append it, if not, check its parent. Then you apply for focusing over here. By the way, this is actually not my original code. This is something I basically modified from somewhere else. But this is something you can use actually as like a model for it. And our graph version is much easier than the original model. Just use zeros and ones for uniquely weighted graphs. There's basically a very simple 0 1 matrix here. We have a sync equal to 5 because we have a total of 5 different layers. And then here's what gets interesting. I use this is terrible runtime, but it actually works really well for focusing. So it's 4 for loops, but only running an O n time because you basically do the same thing like n times. And if you run this, eventually you'll get all the max flows to be 1, which is perfect. You want to have 1 because any path is the same in this particular graph up here. For part B, we basically determine the values. So once again, I got to fix the typo here, but you get the point. And I find it determined rather easily, as I mentioned before, should be pretty simple, 121. And I basically made some very small functions to determine the true positive rate, false positive rate, true negative rate, false negative rate, using the formula from before. Here's what gets interesting. I use some geometric answers here and recalculate this carefully, which means I basically recalculate the whole area outside of these two functions, and I actually add in this value here. The reason why I add in this value because there's some error in calculation due to sig figs. But with the actual, accounting for the error part, it'll calculate the proper 0.506 instead of the original whole area, which is actually incorrect. So you have to be careful with some of the numbers you use in Python. Finally, you got part C, which, talking about the ROC curve. And this is actually frowned upon for the ROC value, because nobody's not supposed to change. Like the curve can change, but ROC AOC value itself, it should not be changing per run. That's something I would actually fix in a bonus episode. But since I was running low on time for this one, I decided just to simply slap together a ROC AOC curve, feed to my Northeastern data mining class, and use, of course, the average data set to figure this out. And here's what I'm talking about, the rabble stuff. So yeah, this is the y-test.rabble and y-square.rabble. It's very important. You interpolate all the ROC curves at the point, and you finally plot the beautiful curve and look at how the Shang Chi colors look. Look fantastic, right? Looks pretty fire. Finally, part D, you have, the 4 different classifiers. So you have basically a bunch of imports here. I imported a couple of things here to make sure the code doesn't give any warnings, but generally you don't want to always hide away the warnings because warnings can give you some insight where your code is going wrong. They have the learning models, and you have something to actually do is called binarizing the data set, or turning from a multi-class to a 2-class 0-1 data set. And of course, because this thing's not using SMOTI at all, this means significant overfitting here, which we can deal with in the episode 10 with SMOTI. And basically run the whole thing again, binarize some data, add some noisy features to make this thing more interesting. And this is clearly overfitting here with the decision tree of 1. Logistic regression looks a lot better, actually. And my apologies, I have to actually name something here. So yes, this is why you have to be very careful with the code you use. Anyway, yeah. These I call my own bug, my own code. Anyway, I basically plot a nice looking precision recall curve here. And this is looking really good. So then I have a precision recall here. This curve, almost a perfect interhyperbola, which is quite nice. And then finally, support vector machine, which is like a bit of a unusual solution. We have an ensemble of support models to both analyze classification and regression analysis. So just a quick drawing over here. So you have basically support model 1 here, 2, 3, up to n. And what the machine basically does is, I'm gonna change colors here. What the machine basically does is the following. The machine basically has a box of different models, the SVM machine. And what we basically do is we check for each of the models, does it actually run in an ensemble? If it runs, we are good. If it does not run, we're going to go back to previous ensemble value. So for this particular machine, you have to be very careful with where you're putting things. Luckily for us, we only have one ensemble for this particular support vector machine. So if we keep on running this, it'll basically give you a solid position score of 0.88. And I talk about the more powerful models down here again. It's a rehash of the slide deck. And the epilogue is, doesn't matter what model you use, really. It just comes down to what is your data? Is your data something that you can use with one model, two model, or in the case of my project from Northeastern, even 3 models? So ROC curves are just a great way for you to show visually what's going on with the models and with the data. So here is now the preview of episode 7. So you can see it talks about clustering a little bit, which is another great data science topic about like graph algorithms. And of course, it's going to go to Teen Titans, a little bit of childhood classics. And then we talk about stable matching as a form of graph algorithm as well. So it gets into a little bit more into NP now with graph code. So yeah, see you guys in October. Hope I enjoyed Hawaii. And of course, like and subscribe. Yes, once again, apologies for no guest collab, but it's all good. So yep, enjoy your Zhongzhou or Mid-Autumn Festival. And of course, continue to stay safe during this time. Thank you.